So today I am going to deliver a lecture on deduction of gas laws from kinetic theory of gases. Myself, Dr. Sanjay Gauri, Head and Assistant Professor in Department of Physics, Dr. Ambedkar College, Chandrapur. So in my presentation, I will introduce the kinetic theory of gases. After that, we will see the deduction of the Boyle's law from the kinetic theory of gases. Then deduction of Charle's law from kinetic theory of gases. Then deduction of pressure law from the kinetic theory of gases. Deduction of ideal gas equation from kinetic theory of gases. And lastly, I will discuss about the speed distribution curve of the ideal gases. So first of all, last time we have seen the what is ideal or perfect gas. So what is the perfect gas or ideal gas? That you have studied in the 12th. The gas which perfectly obeys gas laws such as Boyle's law, Charles law, pressure law is the perfect or ideal gas. You have also studied the ideal gas equation. What is that ideal gas equation? PV is equal to nRT, where P is the pressure, V is the volume, and T is the temperature of the ideal gas. And N is the number of moles, and R is the universal gas constant. In actual practice, no gas is the ideal one. However, in practice, we will consider the oxygen, nitrogen, helium, hydrogen are the ideal gases at ordinary temperature and pressure. Why these gases are called the ordinary ideal gases? Because these gas molecules should obey the gas laws at all temperature and pressure. But the example that I have quoted here, oxygen, nitrogen, helium and hydrogen, these are the gases which obeys the gas laws at ordinary temperature and pressure. Other than this ordinary temperature and pressure, the gas law is not obeyed by the ideal gas molecules. Then we have also seen the expression for the pressure exerted by the molecule of the gas. You have also derived this expression in the 12th standard. So for that purpose, consider a given mass of ideal gas enclosed in a cubical vessel. Then the expression for the pressure exerted by the molecule of the gas on the wall of the container or vessel is given by P is equal to 1 by 3 m into n upon V into C bar square. This is the equation number 1. So this is the one form of the expression for the pressure exerted by the molecule of the gas. Here m is the mass of each molecule of the gas, n is the number of molecules of the gas, C bar square is the mean square velocity of the molecule of the gas, and V is the volume of the cubical vessel or container. So the same expression we can write in a different manner as P is equal to 1 by 3. Instead of this Mn, we will substitute the capital M upon V into C bar square. So this is the another form of the pressure exerted by the molecule of the gas. Then we will see the third expression, third form of the ideal gas expression. So P is equal to 1 by 3 into rho into C bar square, where rho is the density of the molecule of the gas and C bar square is the mean square velocity of the molecule of the gas, and V is the volume of the cubical vessel or cubical container. Then we will deduce the Boyle's law from the kinetic theory of gases. According to the Boyle's law, the pressure of a given mass of a gas is inversely proportional to its volume at constant temperature. Mathematically, we can write the Boyle's law as P is proportional to the 1 upon V, where P is the pressure and V is the volume at constant temperature. And from this we can write it as PV is equal to constant. From this is the expression number 1. From kinetic theory of gases, the pressure of an ideal gas is given by P is equal to 1 by 3 m into n upon V into C bar square. From this expression we can write it as PV is equal to 1 by 3 m into n into C bar square. It is equal to, I will write this same expression in different manner as 2 by 3 into 1 by 2 m into n into C bar square. So, if suppose temperature is the constant, then the average kinetic energy is the 1 by 2 m into C bar square. So, if the temperature is the constant, then average kinetic energy 1 by 2 m into C bar square of the molecule of the gas will be constant. And for a given mass of a gas, n, that is the number of molecules, will also be the constant. In 1 mole of a ideal gas, how many molecules are present? In 1 mole of a ideal gas, the Avogadro number is nothing but the number of molecules present in the ideal gas. And in 1 mole of ideal gas, Avogadro number is 6 into 10 raised to the power 23 molecules per mole. So, the large number of molecules are present in 1 mole of a ideal gas. And therefore, from this expression number 2, we can say that for a given mass of a gas, n is a constant, and at constant temperature, average kinetic energy of the molecule of the gas. Wait for some time, because some students are there in the lobby, so I will allow these students. उशिरा येतात मग जॉईन व्हायला प्रॉब्लेम. नाही, काल केलं होतं आम्ही एन एस सरांच्या विषयामध्ये केलं. काहीतरी प्रॉब्लेम. उशिरा येतात मग प्रॉब्लेम. So, from this equation number 2, we get PV is equal to constant at constant temperature, and this is nothing but the Boyle's law. From this expression we can write it as P is equal to constant upon V, which is the Boyle's law. So, thus we have derived the Boyle's law from the kinetic expression for the pressure exerted by the molecule of the gas, and this expression is obtained by using the kinetic theory of gases. After this Boyle's law, we will deduce the Charle's law from the kinetic theory of gases. According to the, you have studied this Charle's law again in the 12th standard. So, what is the Charle's law? What is the statement of the Charle's law? Anybody please? Do you know the Charle's law? So, according to the Charle's law, volume of a given mass of a gas is directly proportional to the absolute temperature at constant pressure. So, mathematically we can write this Charle's law as V is proportional to the T. V is the volume, T is the absolute temperature of the gas at constant pressure. So, we have seen the expression for the pressure exerted by the molecule of the gas. So, from the kinetic theory of gases, the expression for the pressure of an ideal gas is given by P is equal to 1 by 3 m into n upon V into C bar square. So, from this expression we will write it as V is equal to 1 by 3 m into n upon P into C bar square. The same expression I will write in a different form as 2 by 3 into n by P into 1 by 2 into m into C bar square. And this 1 by 2 m into C bar square is nothing but the average kinetic energy of the molecule of the gas. So, this is our equation number 1. But average kinetic energy of the molecule of the gas is given by 1 by 2 m into C bar square is proportional to the temperature. So, average kinetic energy of the molecule of the gas depends upon the temperature that we have seen in the kinetic interpretation of the temperature. So, 1 by 2 m into C bar square depends upon the temperature, and if suppose this from this if we substitute this value of 1 by 2 m into C bar square proportional to the temperature as 1 by 2 m into C bar square, it is equal to alpha into T, where alpha is the constant of proportionality. Okay, we have removed the proportionality sign, and instead of that we have considered this proportionality constant as a alpha, and therefore we can write this expression as 1 by 2 m into C bar square, it is equal to alpha into T. So, we will substitute this value of 1 by 2 m into C bar square in the previous expression, and therefore we get the equation number 1 as V is equal to 2 by 3 into n by P into alpha into T. Okay. So, here in this expression n is the number of molecules, so it is the constant. Then alpha is the constant of proportionality, it is also the constant. Only the volume of a ideal gas depends upon the temperature and pressure. Okay. So, if suppose we will assume that the pressure is a constant, then we can write it as V is proportional to the T. So, for a given mass of a gas, N will be the constant, and hence at constant pressure for a given mass of a gas, V is proportional to the T, and this is nothing but the Charle's law. So, this is happening only when the pressure is the constant. So, this is the Charle's law. Thus, we have derived the Charle's law from the kinetic theory of gases. Then after this, we will deduce the pressure laws from the kinetic theory of gases. So, according to the pressure law, the pressure of a given mass of a gas is directly proportional to the its absolute temperature at constant volume, and therefore we can state this pressure law mathematically as P is proportional to the T. P is the pressure and T is the absolute temperature. So, P is proportional to the T at constant volume. From kinetic theory of gases, the pressure of an ideal gas is P is equal to 1 by 3 m into n upon V into C bar square, and therefore P is equal to 1 by 3 mn upon V into C bar square, it is equal to, we will write this same expression in different manner as 2 by 3 n upon V into 1 by 2 m into C bar square. And what is this? 1 by 2 m into C bar square? It is nothing but average kinetic energy of the molecule of the gas. So 1 by 2, so the average kinetic energy of the molecule of the gas is 1 by 2 m into c bar square is directly proportional to the temperature, and this is from the kinetic interpretation of the temperature. So average kinetic energy is directly dependent on the temperature of the gas, and therefore we will remove the proportionality sign and we can write the above expression as 1 by 2 m into c bar square, it is equal to alpha into T, where alpha is the constant of proportionality. From equation 1 we get P is equal to 2 by 3 into n upon V into alpha into T. So here again pressure depends upon what? So n is the number of molecules, it is the constant. Alpha is the constant of proportionality, it is also the constant. So the pressure of an ideal gas depends upon the temperature and the volume. For a given mass, n will be the constant, and hence at constant volume, for a given mass of a gas, pressure is directly proportional to the temperature at constant pressure, and this is nothing but the pressure law. So P is the pressure, T is the absolute temperature, pressure is directly proportional to the temperature at constant . This is the pressure law. So here it should be the constant volume. So at constant volume, pressure is directly proportional to the temperature. This is nothing but the Boyle's law. This is nothing but the pressure law. Now we have derived the Boyle's law. We have also derived the pressure law. We have also derived the Charle's law. Now we will derive the ideal gas equation from the kinetic theory of gases. So from the kinetic theory of gases, the expression for the pressure exerted by the molecule of the gas is given by P is equal to 1 by 3 m into n upon V into c bar square. This is the equation number 1. For 1 mole of ideal gas, n is equal to capital N. What is capital N here? N is the small n is the number of molecules, and capital N is the Avogadro's number, and this Avogadro number is the constant. So the value of this Avogadro number is 6 into 10 raised to power 23 molecules per mole. Means in 1 mole of ideal gas, the number of molecules present are the 6 into 10 raised to power 23 molecules per mole, and therefore P is equal to, instead of this small n, we will write here the capital N, because the number of molecules present in the 1 mole of ideal gas is nothing but capital N, and capital N is nothing but the Avogadro's number, and therefore we can write it as P is equal to 1 by 3 m into capital N upon V into c bar square. So this is the equation number 2. Now we will write it as PV. We will cross multiply by this V, then PV is equal to 2 by 3 into 1 by 2 m into n into c bar square. So this is the equation number 2. But the average kinetic energy of 1 mole of one molecule is 1 by 2 m into c bar square is proportional to the temperature. Average kinetic energy depends upon the temperature, and therefore 1 by 2 m into c bar square, which is the average kinetic energy, it is equal to alpha into T. So, where alpha is the constant of proportionality. From this, equation number 2 becomes PV is equal to 2 by 3 n into alpha into T. And here, instead of this bracket term, which is the 2 by 3 into n into alpha, we can write the another constant as R. So, 2 by 3 into n into alpha, it is equal to R, and this constant R is known as universal gas constant, and therefore we can write this above expression as PV is equal to RT. So, this is nothing but the ideal gas equation for 1 mole of a ideal gas. If we consider the n number of molecules or n moles, then PV is equal to n small n RT. So, here we have considered only one mole. Therefore, this expression will be the simplified expression, and it will be PV is equal to RT. So, this is the ideal or perfect gas equation for 1 mole of a ideal gas. So, after this, we will see the discussion on the speed distribution curve. So, here there is one Maxwell speed distribution function, and this Maxwell speed distribution function is given by n of c is equal to 4 pi in bracket m upon 2 pi kt raised to power 3 by 2 into c square into exponential of minus m into c square upon 2 kt, where n of c is the number of molecules having the speed c. So, this n of c is the function of this c. C is nothing but speed of the molecule of the gas. M is the mass of a molecule of the gas. Small k is the Boltzmann's constant, and T is the absolute temperature of the gas. At C is the speed of the molecule of the gas. So, this function, this is the function of speed. This n number of molecules depends upon the speed of the molecule of the gas, and this expression is known as the Maxwell speed distribution function. Okay. So, here this Maxwell speed distribution function I have taken directly, because the expression for that is the very lengthy and it is not important from the examination point of view. So, only this speed distribution function is required for explaining the further topic. So, if we plot a graph, this is the Maxwell speed distribution function. If we plot a graph between n of c, means number of molecules having the speed c with the speed c. So, if we plot a graph between the n of c and speed c, then that graph will be as shown in this slide. This one curve is for the given temperature T1, and the another curve is for the another temperature T2, and this is the third curve for the temperature T3. Here the temperature goes on increasing from T1 to T3, and here this n of c, Maxwell speed distribution function, depends upon the c, that is the speed of the molecule of the gas. So, in the translational motion means motion of a molecule in a straight path. It is moving from one place to the another place. Molecule of the gas are moving from one place to the another place. So, such motion is nothing but a translational motion, and in the translational motion, no molecule is having the zero speed at any temperature. We have seen previously in the kinetic interpretation kinetic interpretation of the temperature, that if the temperature is 0, then the speed of the molecule of the gas is 0, means the molecule of the gas will be at rest. But this state will not be happening. This case is not happening because none of the molecule of the gas, ideal gas, is at rest. They are having the speed 0. So all the molecules of the gas, ideal gas, are moving with speed from low speed to the very high speed. So this is the curve of the n of C, number of molecules having the speed C. So for lower value of C, there are the two terms in the n of C. Which are the two terms which is depending upon the speed? So one term is the C square, which depends upon the speed of the molecule of the gas, and another term is there, that is the exponential term, and this exponential term is exponential of minus m into C square upon 2 kT. So these are the two terms, one C square term and another term is the exponential term. These two terms depends upon the speed of the molecule of the gas. So for any curve, for lower value of C, the term C square is the more effective than the exponential term, and therefore as C increases, here you can see, so for lower value of C, the C square term is the more effective than the exponential term, and therefore as the speed of the molecule of the gas increases, the number of molecules goes on increasing up to this particular value. So for corresponding to this peak value, C is equal to Cm. We will consider that value of speed as Cm, and this Cm is nothing, at this particular C is equal to Cm, the number of molecules is the maximum. So corresponding to this peak, the number of molecules will be the maximum, and this value of C is nothing but Cm, and this Cm is called the most probable speed. What we call this Cm as? This Cm is nothing but the most probable speed. It is the maximum speed of the molecules of the gas having the very large number of, maximum number of molecules. Then as the speed of the molecule of the gas further increases beyond this Cm, so this is the particular value of C. For this particular value of C, C is equal to Cm, and if we increase this speed of the molecule beyond this Cm, then in this case the exponential term is the more effective than the C square term, and therefore the number of molecules decreases exponentially, because beyond the particular speed C is equal to Cm, as we increase the speed of the molecule of the gas, this exponential term is effective, and therefore this number of molecules decreases exponentially. So this is seen from each curve. कोई भी एक कर्व आप लेंगे तो उस कर्व के लिए क्या होगा, पहले तो जैसे जैसे स्पीड इंक्रीज होते जाएगा, नंबर ऑफ मॉलिक्यूल्स गोज ऑन इंक्रीजिंग, and this number of molecules reaches to the maximum value at a particular speed. C is equal to Cm, and if we increase the beyond the Cm, if we increase the speed beyond the Cm, then the number of molecules goes on decreasing. Then as the temperature of the gas increases, the most probable speed also increases. The range of the speed is greater. As the temperature increases, the curve becomes the broad. You can see here, this is nothing but particular Cm for a given temperature, T1, and this is the speed having the this is the maximum speed of the molecule of the gas for a temperature T2. Here temperature goes on increasing from T1 to T3. So you can see that for the temperature T1, the maximum speed is the C1. Then for the temperature T2, the maximum speed or most probable speed is for the temperature T2 is the somewhat higher. Then again if the temperature is increased, again the most probable speed of the molecule of the gas increases. So for this temperature T1, it will be the maximum speed, most probable speed. For the temperature T2, most probable speed will be the higher, and again as the temperature T3 increases, then most probable speed also increases. Then fifth conclusion that can be drawn from this curve, as at a given temperature, you can take any curve. So for any curve, the area under the distribution curve is equal to the number of molecules in the gas. So area under the curve is nothing but n, that is the number of molecules present in the ideal gas. So it is given by n is equal to integration from 0 to infinity n of C into dC. So this is nothing but with the help of this expression we can obtain the number of molecules present in the ideal gas at a given temperature. So with the help of this expression, n is equal to integration from 0 to infinity n of C dC. With the help of this expression, we can obtain the number of molecules, and these number of molecules present at a number of molecules present in the ideal gas at a given temperature is nothing but the area under the curve. So we can take any one curve. So the area under the curve is nothing but the number of molecules present in the ideal gas. So here this I will end this today's lecture. समझ में आया आप लोगों को?
यस सर।
कुछ दिक्कत होगी, कुछ समझ में नहीं आया होगा तो आप